Hello, welcome to another problem session. And We have a problem today that can be said to be between elastic. It's a problem in elastic collision and spring motion. It's kind of combined. So a couple of things to know before we do the problem is what the problem is actually, how many time steps or kinds of different things that happen in the problem. So this block, let's call this block M1 and this block M2, and so this is before the collision, and then so this is like a T1 at this time, and then there is it comes and there is at some point there is a collision. So it is a 2 meter per second, and this is 0. This is at collision. So let's call it T2, and then at some then there's a point later on. This thing is moving. Presumably, I'm going to assume this is moving this way. So let's call it V1 prime. And then this block is the spring is compressed, and this is moving this way. So if I call this T equal to 0, let's call this T equal to 0 instead of T2, then we're supposed to find out. So this is kind of reference place. So this will go. This will go all the way somewhere here and then return, right? It used to be here, it will go all the way here and then return. Presumably it's going to go oscillate like that. Okay. So the question is, this is a half period, right? So this is the half period, so it goes and returns at that time. So let's call that at that time T3 or T. We're going to call T. It has gone. It has returned from making this one period return or half a period returned, and at that point this block 1 and this block 2, block 1 is at that distance, and that distance is D. That is what we're supposed to find. So that's what we're supposed to find. So looking at it this way, we need to look at this, what happens in collision. So this is elastic collision, and after the collision, if you look at number one is actually moving. After the collision, number 1 moves from here to here at the constant speed V1 prime. So if I know this T is half period, okay, so the D will simply be V1 prime T over 2, right? So how do I know half a period? You need to know from someplace else, or maybe your studies of the spring motion. You need to know that if I have a K and M, then the period T is 2 pi square root of M over K, and this is M2 right now. So you have to know this. Maybe you know in terms of omega, angular frequency is square root of k over m, and then that is t is 2 pi over omega. So however you know it, you have to know that this is very, if you don't remember this, it's not going to be easy to do. All right. Okay, so let's see you know this. And so our strategy is, you can see we know t because we know m2 and k, so we know t. So we know t. So thing to find is v1 prime. And v1 prime is the speed after an elastic collision. So the task is find v1 prime after the elastic collision. So you can see that elastic collisions, I don't have to worry about the spring. You can just forget there's a spring. So we can just forget there is a spring, because spring is not participating in it, right? Because collision is at the instant, right? So, and this at that instant, spring is neither compressed nor extended. So it's not making any taking any part in it. So so let's always when you do collision, let's use a coordinate system. So this is before the collision. This situation is before, and this thing is v1, and this is v2 equal to 0. All x coordinate. This is all positive x coordinate. So this and then after the collision, we are saying that this is speed is v1 prime this way. So this is so v1 x prime is minus v1 prime. This is minus because of coordinate here, and v2 is some v2, and so v2x equals to v2 plus and minus here, right? So two things. One is momentum conservation. Momentum gives me m1. You can already see the adding momentum. This guy is minus m1 v1 prime plus m2 v2 prime. These are primes. Prime equals to m1 v1. And then elastic collision, I can write down kinetic energy after equals kinetic energy before. So I can do either kinetic energy after equal to kinetic energy before, or we can do relative speeds ratio equal to 1, because it will be coefficient restitution will be 1 for elastic collision, right? So we'll just do this. So you can see that relative speed will be v2x minus v1x. So it's going to be v2 prime minus v1 prime, and that's going to be positive, equals to relative speed. If you can 0 minus v1, that would be 0 minus v1, and they should be equal to each other, right? So, and there's no mass or anything here, so this is a very nice equation. So we can write down v2 prime. Actually, this will be plus, because minus minus becomes a plus v1 prime equals to v1. So I use prime for after and non-prime for before. So this is, let's see, equation 1 and this is equation 2. You can clearly multiply. I want v1, right? I don't need to care about v2, so I need to get rid of v2. To get rid of v2 prime, all I have to do is multiply this by m2 and subtract. So, and subtract 1 from 2. So this minus that. So on the right side, I'm going to get m2 minus m1 v1, and on the left side I'm going to get m1 plus m2. So this m2 and m1 plus m1 v1 prime. Okay, so v1 prime is just m. Now I can put the numbers because I already can see the answer of v1, and that's an m2 minus m1 is 1, and this is 3, and v1 is 2. So 2 over 3 meter per second. So we got this also. So let's get the numerical value for t. So numerical value 2, and then we'll be done, right? So this is, and the t is just 2 pi square root of m2 over k, and k is this, and m2 is 2, so this is 2 pi, just 2 pi. And so now we use the d, so the d equals to 2/3 times 2 pi, or 2 pi over 2, which is 2 pi over 3, and that's the meter. And I can just use a calculator to get the final answer, and that is 2.09 meter. So that's the answer. Okay, so after a problem, you should kind of go back and look at the problem, what was done. So the first step we had to do was kind of walk ourselves through the kinds of events that we need to worry about, right? So this is very important walkthrough. This is walk through the problem is very important, and because it gave us like, okay, at this point it has a collision, and then we needed to actually get the time it returns, but that's actually it's going to keep going back. So we need half the period, and once we recognize half the period, we can use the formula that you may have memorized from before of a block attached to a spring mass system. This formula was important to know. And then the last was that after the collision, this thing is moving uniformly. So after the collision, a uniform motion, because unlike this is attached and subject to some force, but the block 1 was free to move. It had no horizontal force. There's a vertical gravity and normal force balance, but then we're not concerned with that. So that was another. And then we isolated what we need to find. So it became, we need to find the speed after. And then the rest, is very straightforward. Setting up the momentum conservation. You can see here they have two unknowns. And then elastic, we had a elastic collision condition, which is kinetic energy conservation, or you can alternatively write in relative speed. And we have to be careful writing this out because you can make a plus minus mistake around here. All right, so that's the summary of it. Don't forget to subscribe to this channel if you like it, and more at this website. So I'll see you in another video. Bye.